Happy Wednesday morning. We have to find zeros of polynomials. So there are several theorems we need to do this. First up, the remainder theorem, which states if a polynomial is divided by x minus k, then its remainder is the value f of k. This also allows us to evaluate polynomials in a much simpler way. Just divide the polynomial by x minus whatever the value is. Its remainder is what you're looking for. This leads into the factor theorem. States that k is a zero of f of x if and only if x minus k is a factor of f of x. Combining that with the remainder theorem allows us to say that x minus k is a factor of f of x if and only if f of k is 0. The rational zero theorem, this is a really important one. You have a polynomial with integer coefficients. Every rational zero of f of x will have the form p over q, where p is a factor of your constant and q is a factor of your leading coefficients. And so typically this is the first thing we do when we're trying to find zeros, is we just list out all the possible rational zeros by looking at factors of the constant over factors of the leading coefficients. One of the most important results out of algebra, called fundamental theorem of algebra. They'll be posted up. Okay. I can't really go back because it's going to take a long time to find the zeros. Okay. But they will be posted online, so you don't have to worry about it. Okay. That's why I recommend just write down like important stuff in class, and then you can go back and finish it.
Yeah. Thank you.
of x is a polynomial with degree n greater than 0, f of x has at least one complex 0. Now remember, actually I don't know if this is going to be a remember. Think of a real number. Call it, I don't know, let's use my favorite number, 28. My favorite integer, 28. Now let's see if you're paying attention. You might ask that as an extra credit question.
28.
I'll let me repeat myself.
I wrote it down.
Is a real number complex? So complex numbers can be written in the form of a plus bi. Those are the definition of the complex numbers. Right, a plus bi, where a and b are real numbers, I squared is defined to be minus 1. So the question is 28 a complex number? Can it be written in the form of a plus bi? That was very tentative. But I'm still going to give it that you said yes. How can you represent it as a plus bi? You're overthinking it. Every real number is complex. Which means that the fundamental theorem of algebra isn't saying that you're going to have at least one 0 that has the imaginary component. A real number is complex. We can reword this to say that if f of x is a polynomial of degree n greater than 0, and a is a non-zero real number, then f of x has exactly n linear factors. In other words, you can represent f of x as a times x minus c1 times x minus c2, so on and so forth, down to times x minus cn, where each of your c sub i's is a complex number. In other words, your polynomial has exactly n zeros if you count for multiplicities. That means if you're trying to find the zeros, all the zeros of a 5th degree polynomial, when counting multiplicities, you're going to have 5 of them. It doesn't tell you how many are going to be real numbers and how many are going to be complex with the imaginary component. So when I say complex, I mean with a non-zero imaginary. Fortunately, for the most part, in your calculus studies, you're only interested in the real zeros, which means this theorem is useless. Because it doesn't say that there's exactly n real zeros. It says there's exactly n complex zeros. Complex conjugate theorem. If a polynomial function has real coefficients and a complex zero, then the complex conjugate of that zero is also a zero. So complex zeros always occur in pairs. If a plus bi is a zero, so is a minus bi. Again, important to note that all the coefficients are real. Once you start dealing with a complex polynomial, this doesn't hold. Have a lucky for you, we won't be dealing with such situations in this course. All of our coefficients will be reals. Descartes' rule of signs. Again, this is an important one. You're given a polynomial with real coefficients. The number of positive real zeros is either equal to the number of sign changes of f of x, or is less than this number by an even integer. The number of negative real zeros, either equal to the number of sign changes in f of negative x, or less than this number by an even integer. Quadratics, you know how to solve. So I'm going to skip all of those. All the polynomials we will look at will be in degree 3 or larger. Generally speaking, if you have a polynomial that you can easily factor, i.e. its quadratic form, or can be factored by grouping, do it. Because it is going to take a lot less time to do that than the method that we're going to go over now. pay close attention to what the question is asking. If it says find all the zeros, I want both real and complex. If it's asking just for the real zeros, you can ignore the complex ones. Start by listing out your possible rational zeros. What's your constant? So just look at 24. What are the factors of 24? Is that all of them?
12, 2, 6, 4, 8,
8, 1.
3.
What else? You missed the obvious ones. 1 and 24. 1, 2, 3, 4, 6, 8, 12, and 24. That's actually only half of them. They're negatives as well. Which is why I said ignore the negative 24. What about the leading coefficient? What is it? 1. Oh, that is beautiful. Because remember, rational zeros theorem says that it's P over Q, where P is a factor of the constant and Q is a factor of the leading coefficient. Leading coefficient only has one factor, 1. So if we have rational zeros, it's going to be one of those. Also keep in mind that there's nowhere that says it has to be a rational zero. So you could get extremely unlucky and it has no rational zeros, and then you cry. Now use Descartes' rule of signs. Look in f of x. We want to count the number of sign changes. Coefficient, positive or negative? Coefficient, positive or negative? That's not a sign change. Coefficient, positive or negative?
Negative.
That's now a sign change. There's 1. Coefficient, positive or negative? One sign change. There's one positive real zero. Or less an even number. But what's 1 minus 2? Negative 1. You can't have a negative number of real zeros, which is why we know there's exactly one positive. For the negatives, you want to look at f of negative x. So here's what I'm going to do. Odd powers of a negative are negative, right? Even powers become positive. So all of your odd powers are going to change signs. That stays plus, that stays minus. Now count the sign changes. Negative to positive is 1. To positive to negative is 2. there are two sign changes. So there's either two negative real zeros or less an even number. 2 minus 2 is what? So there's either two negative real zeros or no negative real zeros. And again, keep in mind, this is accounting for multiplicities. This is counting multiplicities. Now we're going to use the fundamental theorem of algebra to make a chart of all the possible combinations we can have. Positive reals, 1. You could have two negatives. So determine the number of complex this will give you. What's the degree of our polynomial? So the sum of each row has to be 3. So if you have one positive real and two negative reals, how many complex do you have? Zero. 1 plus 2 is 3. You've already counted for all of your zeros. Next scenario, you have one positive real and no negative reals. How many complex do you have to have? I heard it over here. How many did you say?
You need 2, right?
2. One plus 2 is 3. Now just make sure that you did that right. Remember, complex zeros have to occur in pairs, which means you can never have an odd number of complex zeros. Is 2 odd? No, so that's not a contradiction. Is there any other possible combination? No, because you have to have one positive real. That accounts for all the possible combinations. So when we find all of our zeros, we're going to have to match one of those two rows. One positive and two negatives, or one positive and two complex. Now comes the unfortunate part. Testing your rational zeros to see what, or testing those rational numbers up there to see which one is a 0. This is where if you get extremely unlucky, this can take you a while. I try to be systematic about it. So look at the table we just generated. In both cases, we have to have a positive real. So I'm only going to look at those positive numbers, because I know that I'm going to have a positive real. I just hope that it's rational. What does it mean to be a 0?
Y value is 0.
Plug it into the function, it gives you 0. Which by the remainder theorem means when you divide it by x minus k, your remainder is 0. That's what we're going to do. So we're going to use synthetic division. So here's how I'm going to set it up. coefficients for f of x. I'm going to set them up like that, and then I'm going to do all of my test values along here. This way, I'm not, writing out a synthetic division every single time. I just kind of do it in one table. Start with 1. So we're going to divide by x minus 1. One comes down, times 1, plus 3, times 1, plus negative 10, times 1, plus negative 24 is not 0. I think it's negative 30, right? 1 is not a 0. Well, then I'll try 2. One times 2 plus 3 times 2 plus negative 10, which means this is not going to be a 0. You're going to have a remainder of 24. Negative 24. All right, we'll try 3. 1 times 3 plus 3 times 3 plus negative 10 times 3 plus negative 24, we have a 0. Which means 3 is a 0, making x minus 3 a factor. Factor it out, what are you left with? It's staring you right in the face. So if you factor it out, that means x minus 3 is your divisor. What remains is your quotient.
X squared plus 6x plus 8.
Oh. That's quadratic, right? We can solve a quadratic. So we don't have to go through this process again. Can x squared plus 6x plus 8 be factored?
Yeah.
What does it factor to?
X plus 2 and x plus 4.
Those are zeros. Negative 4, negative 2, and 3. And again, using the factor theorem. Now just make sure that your math is right. Does that match one of the two scenarios we came up with? It does. 1 positive, 2 negatives. It's the first row. And there are 3 of them. Not a difficult process. It's just very long and very tedious. Which means there's a lot of opportunities to make an arithmetic error. You can verify this by plotting it. And looking on the x-intercept, looking for the x-intercepts on your graphing calculator. Keep in mind that that's only going to give you real zeros. And it won't give you multiplicities. Although if you're clever enough with knowing how functions look, you can kind of figure out the multiplicities. It won't ever give you complex zeros. Once you're able to use a calculator that has symbolic manipulation, you can also use it to solve for zeros of any function. Which will make, once you're done with this process, make you appreciate that feature a lot more. So now imagine doing this for a 10th degree polynomial. Imagine getting unlucky enough where none of those numbers listed there is a 0, which means you don't have any rational zeros. So start off with your rational zeros. What is the constant? Factors of 18 are what? 1, 2, 3, 6, 9, 18, and they're negatives. What are the factors of the leading coefficient? So what's the leading coefficient? What are its factors? And then they're negatives. Well, again, 1's one of them. So list those out. Now take each of those and divide it by 3. Because 3 was a factor of the leading coefficient. So 1/3, 2/3. What's 3 over 3? We already have it listed. Skip it. What's 6 over 3? What's 9 over 3? What's 18 over 3? Those are already all listed, so there's no need to relist them. These are all of your possible rational zeros. $16 of them. How many positive real zeros are we going to have? Remember, it's the number of sign changes in f of x less an even number. You count 3 sign changes. There's 1. So we're going to have 1 positive real. What about negative reals? And so remember, even powers keep the sign. Odd powers are going to change the sign. How many sign changes do you see?
3.
So how many negative real zeros are we going to have? All right, what did Descartes' rule of sign say? It's going to be that number less than even. So 3 or 1. So we have to have one positive. We could have 3 negatives, which gives us how many complex? Or we could have 1 negative, which would give us how many complex? Those are the only 2 possible combinations. So now we have to check. Here we know we're going to have 1 positive and at least 1 negative. What are the coefficients? So let's start with 1. Three times 1 plus 16 times 1 plus 20 times 1 plus negative 9 times 1 plus negative 18. Is 1 a 0? Nope. Let's try negative 1 now. Three times negative 1 plus 16 times negative 1 plus 20 times negative 1 plus negative 9 times negative 1 plus negative 18. Oh, we were so close. But that's not a 0. Well, what about 2 then? Really hoping it's not a fraction. 3 times 2 plus 16 times 2 plus 20. Oh boy, this is getting off the rails. Times 2 plus negative 9. Yeah, I don't even have to continue because there's no way in hell that's a 0. 2 times 1, 19 is not 18. cross that off. It's not 0, so I don't care. What about -2? 3 times -2 plus 16 times -2 plus 20 times -2 plus -9 times -2. Yay. That makes -2 a 0. Which makes x plus 2 a factor. So when you factor it out, what are you left with? Keep going. Would you be able to factor that cubic by grouping? The answer is unfortunately no. Bummer. So take that quotient. It's a new function called f1. We now repeat that process for f1. So start off by listing out the rationals. What is the constant? Factors of 9. What's the leading coefficient? Factors. Divide each of those by 3. You only get one new one, plus minus a third. Has to have one real 0, because we haven't found, or has to have one positive, because we haven't found it yet. And then just verify. When you use Descartes' rule of sign, do you get 2 sign changes? You do. Which is good, because we already found one negative real, which means we're going to have 2 or none left over. And I'm not going to worry about making up that new table, because I'm going to use that old one. Now, what do we know about plus minus 1? They're not zeros. They're There's no need to check them. They weren't zeros before, they can't be zeros now. Notice we've also now limited the remaining zeros. We got rid of the plus minus 6, the plus minus 18, and the plus minus 2/3. So we don't have to check those. Also, I know I'm going to have a positive real. So let's just check the positives. Because I'm not guaranteed a negative. Which means we're starting off with 3. What are the coefficients for F1? What was it? Keep going. There's an X missing and then -9. Also, cheat. Look at the last row. Those would be your coefficients. And ignoring the very last one because that's the remainder. Start with 3. 3 times 3 plus 10. Oh boy. Times 3. You don't need a calculator.
57.
57. 3 times 20 is 60. 19 is 1 less than 20, so it's going to be 3 less than 60. Times 3 is not 9. So this is where I'm going to cheat. I'll look at my notes. As it turns out, 9 and 1/3 are not zeros either. Which means your positive real 0 is not rational. It's irrational. So I'm just going to go, pretend like we checked that. We're going to pretend we checked that one, and we're going to cry. So check now the negatives, because we're still we may have a negative left over. And if we don't, then we really cry. -3. 3 times -3 plus 10 times -3 plus 0 times -3. -3 is a 0. So we just found a factor for F1. X plus 3. What's your quotient? So what are you left with? That's the remainder.
3 x squared.
What is it?
What is 3?
What is it?
Squared plus x minus 3.
You're down to a quadratic, which means this process is now done. Oh, by the way, that now gives us 2 negative real zeros, which means you can now eliminate that last row as a possibility. So it's going to have to be the first row. 1 positive and 3 negatives with no complex. Can 3x squared plus x minus 3 be factored? The answer is no. Because if it could have been, we would have found a positive real zero with the rational. Which means you have to use what? How do you solve a quadratic that cannot be factored? Spent probably most of algebra doing this. QF. Quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Remember that? And if not, you better. Negative b plus or minus the square root of b squared minus 4 times 3 is what? Times negative 3.
36. Negative 36.
So we get minus negative 36 all over 2 times 3. What's the square root of 37? Can that be simplified? Is prime, which means it's impossible for it to be a perfect square. The fact that it's prime also means it can't have a perfect square factor. So those are your remaining 2 zeros. Now comes the fun part. There's no particular order you have to list them in. I just have to do it in descending or in ascending order. It's one of my quirks. So I already got negative 3 and negative 2 as zeros. Those are the remaining 2. Negative 1 minus root 37 over 6 and negative 1 plus root 37 over 6. Negative 1 minus root 37 over 6 is the negative real, so those are your 3 negatives. And then negative 1 plus root 37 over 6 would be your 1 positive. That first one is going to be slightly larger than negative 7/6. I'm sorry, not slightly larger, slightly smaller the negative 7/6. And the negative 1 plus root 37 over 6 will be slightly larger than 5/6. Because I know that root 36 is 6. So root 37 is going to be larger than 6.
This is all one question.
That was one problem. And again, that's only a 4th degree polynomial.
Oh.
So I said, imagine having to do this by hand for like a 23rd degree polynomial or something. And not a nice one either that can easily be factored. Right? Not something like x to the 23rd minus 1 equals 0. What's x? That one's easy. 1. I'm talking about one that would have every single term in the polynomial. I'm not going to stop you doing it by hand. I'm not doing it by hand. That's why I invented the computer. Factors of the constant. Factors of the leading. That first row takes care of when the factor is 1. So take each of those divided by 2.
Is that always? My bad.
Because 2 is a factor of the leading, yes.
Right, yeah.
2 over 2 is 1. Already have it. 6 over 2 is 3. We already have it. And 18 over 2 is 9. We already have it. Now, go back up to that first row and divide each of those by 4. Right, because 4 is a factor of the leading. What's 2 over 4? Two over 4. Is it already listed? Ignore it. 3 over 4, we don't have. 6 over 4. What is it? It's already listed. Ignore it. 18 over 4. What is it? Over 4. 9 over 2, it's already listed. Those are all the possible rationals. That's how many of them. That's 24 of them. How many positive real number, or how many positive real zeros could we have? Again, remember, count the sign changes in f of x. So how many sign changes do we have? So how many positive real zeros can we have? Remember Descartes' rule of signs. Number of sign changes of f of x, less an even number. So there are 2 sign changes. 2 less an even number. Two minus 2 is 0. What about negative real zeros? It's 2 less than even. So 2 or 0. Bummer. So if we make our chart of combinations, two positives, 2 negatives gives how many complex? How many zeros do we have to have? What's the degree of a polynomial? So we have to have how many? The degree is 4, you have how many zeros? If you have 2 positives and 2 negatives, how many complex does that mean you have? Don't we already have all 4? You could have 2 positive and no negative, which would mean you have how many complex? You could have no positives and 2 negatives, so how many complex? You could have no positives and no negatives, so how many complex? That is the extremely sad case. That case you cannot solve right now. That requires complex analysis. So let's hope it's not that case. So now we have to start checking. So we start checking those rationals. And again, we hope that the real zeros, at least one of them is going to be rational. Because again, if not, we cry. So now the question is, do I want to go through each one and check? Or do I want to just choose a lucky guess? I think I'll just go lucky. Coefficients. 4, -4, -7, -6, and 18. I'm going to start with 3 halves. Let's see if I get lucky. Four times 3 halves. -4
2.
times 3 halves. You don't need a calculator.
3.
-7
-4.
times 3 halves.
-6.
-6
-12.
times 3 halves. Plus 18. What a lucky guess. X minus 3 halves is a factor. What are you left with? There's F1. Repeat the process. Because that's cubic. What are the factors of 12? Room. 1, 2, 3, 4, 12. Factors of 4, 1, 2, and 4. Go back to the original list. Are there any on this new list that were not on the original? Hmm? Check again. What was it? 12 wasn't on the original. What else wasn't there? Four. That means they can't be zeros. Everything else was on the original list, so that's still fair game. We found a positive real zero, which means we still have one left. So here's what we're going to do. 4, 2, -4, -12. So I'm going to look at the positives here to test. And I don't know, 3/2 worked out pretty well for me last time. So let's try it again. Remember, there's no rule that says it can't happen more than once. So 3/2 could still be a possibility. 4 times 3/2 plus 2 times 3/2 minus 4 times 3/2 minus 12. 3/2 must be my lucky number. X minus 3/2 is a factor of F1. What's your quotient? Isn't there 4 in common? You know, I don't like the way that looks. I like the way that looks better. You don't have to do that. X squared plus 2x plus 2, can that be factored? Which means we have to do what? How do you solve a quadratic that cannot be factored? Negative b plus or minus the square root of b squared minus 4ac all over 2a. This would be a problem. But we're also looking at complex zeros. How would you write the square root of -4? What's the square root of 4? What's the square root of -1? Is that reduced? Can that be simplified? What does it simplify to? So before we list out the zeros, how many x-intercepts does this function have? So how many x-intercepts are there? Guess I'll be nice and make it multiple choice. 0, 1, 2, 3, or 4. Okay, so we have 4. Someone's saying 2. Okay. Anyone else want to make a guess?
0.
Someone says 0. Oh, throwing a little statistics. Who said 4? What's the probability that you're correct?
You get 5 options, 20%.
Sorry about probability. Who said 2? What's the probability that you're correct? What's the probability that 0 is correct? All 3 of them have 0% probability of being correct. That's not how probabilities work. What you did was find the probability of randomly guessing the correct answer. Once you've selected it, it's either right or wrong. Your probability is either 0 or 100. There's one x-intercept. At 3 halves. 3 halves is a multiplicity of 2, which means it touches it. Doesn't cross it. It's a turning point. Complex zeros cannot be x-intercepts because we're only dealing with the real plane. So here are the zeros. 3 halves. It occurs twice. I don't need to write it twice. Then -1 minus I, -1 plus I. Those would be your 3 zeros. Or 4 zeros, right? Because 3 halves occurs twice. 5 for now. Yeah, nope. Okay, so let's do. There's your plot. So as you can see, there's still a limitation. Because we had one x-intercept, and there's even, which says it touches, so we know it's a turning point. We could easily find the y-intercept. But how do you determine that it does this, instead of just being parabolic and maybe doing this? Pass through there and then just keep going up. You can't with just these techniques. Right, so this is not parabolic. X to the fourth plus 2x squared plus 1. What do you want to do first? Okay, so what are your rational zeros? Makes it easy. Plug them in. Plug in 1, what do you get? What's f of 1? What's f of negative 1? It's also 4. Oh dear. They're not zeros. How would you proceed then? Because the method that we've been doing requires there to be a 0. Requires there to be at least one rational 0. And there are none. You're overlooking something. Well, true. This would have been something you probably looked at in intermediate algebra. Sure it's still showing. Do change a variable. Replace x squared with z. With that variable, x to the fourth becomes what?
2. Like z.
You're right. Z to the 2. Z squared.
Yeah.
What kind of polynomial is that?
Square.
Isn't that quadratic? This function's quadratic form. Can z squared plus 2z plus 1 be factored? What does it factor to? So what's the zeros for z? Set that equal to 0 and solve. What do you get for z?
-1.
What was z?
X.
What was z?
X4.
If x squared is -1, what's x? Just I.
Would be x would be the square root of -1, which is I, right? Plus or,
What is it?
plus or minus that?
Plus or minus I. You forgot the complex conjugate theorem, which says they occur in pairs. I is a 0, which means so is -I. Both happen to be multiplicity 2. So that's 4 total zeros. So what was the purpose of that example? Look for an easier way. Don't always just default to the method we've been using. You should be able to easily recognize quadratic form. Do with that. Another quadratic form, I could have done this. That's quadratic. Let z be x cubed. And then everything would be the same. Z is -1, which means x cubed is -1, so x is -1. Now there's a problem with that. That -1 is multiplicity 3, which means you have 3 zeros left. always try a quadratic form first. Let's do this. We can't factor that by grouping, so list out your rational zeros. Rational zeros. How'd you get them? Factors of 20 is 20. I didn't know there's no more than that. Yeah, factors of 1, 1, so that's it. How many real zeros will be positive? So what did we do to find the positive real zeros?
So sign changes, right?
How many sign changes are there?
2,
So that tells you there are how many positive real zeros.
2 is 0.
What about negative reals?
Could just be 1.
That was one of them. And so possible combinations, 2 positive, 1 negative leaves no complex, right? No positive, 1 negative would leave 2 complex. We have a negative real. We're guaranteed a negative real. So let's just check the negative rationals. I don't know. -5 sounds good. One times -5 minus 2, -7 times -5 is 35 minus 31 is 4 times -5 is -20. Plus 20 is 0. So we can factor f of x as x plus 5 times x squared minus 7x plus 4. Can that be factored? cannot. Quadratic. Negative b plus or minus the square root. B squared minus 4ac all over 2a gives us 7 plus or minus the square root of 33 all over 2. Square root of 33 cannot be simplified. Factors of 33 are 3 and 11. Neither of which are perfect squares. -5, 7 minus root 33 over 2, 7 plus 33 over 2. 2 positive reals, 1 negative. And that last one will be left as an exercise. Questions on finding the zeros of a polynomial? Oh, yeah.
Question: can we always use the like let c equal next number? No, we can't always use it.
Now, that only works if you want to try and get it into some kind of form.
Okay.
So don't forget, you have a quiz that'll be due before the start of next class. And the first exam is Monday. Make sure you bring in a pencil or black ink pen. You will be allowed to use notes. You'll be allowed to use any model graphing calculator that does not have symbolic manipulation.
I got T84.
Have a good weekend.
So